Okay, I have started recording it now. Okay, so yesterday we found out the area of steel and all required for the deck slab. Okay, three parts were there: deck slab, stringer beam, and cross girder. Okay, I hope you have seen my videos, and I hope you have got an idea how to design a steel beam. Okay, so now that some of the concept will be used here. Okay, and that is why without those concepts it will be difficult for you to proceed with the further steps of design of stringer beams. Okay, so that's why I told you to watch those videos. Now till this part I will not be discussing further. Okay, you have already known this one, live load and dead load for deck slab. That is done. So let us go to the stringer beam. Stringer beam, as I have already told you, the stringer beams are falling in this manner. If you look, if I show you once more, if you look into the top view, so this is the width of the deck slab. .5, and this is the length 4.2 for one panel, and the stringer beams are placed in this manner, like this. In this manner the stringer beams are placed. These are the and for analysis what we have done, we have taken one particular panel which is 1.875 and 4.2, and we move from this side. Okay, people move like this. Okay, so the length, obviously then length of stringer beam will be how much? 4.2. Length of stringer beam will be 4.2 meter because it is going along this direction. Okay, so now dead load from the deck slab, it is taken by what? The dead load that we have calculated, okay, into what? We are finding it in the form of UDL. Okay, so what we have done is from the deck slab, from this, one second. If this is the deck slab, already we have got 6.5 kilonewton per meter square. So into, if I multiply with 1.875, 6.5 kilonewton per meter square multiplied by the width. Okay, this is the deck slab I am referring to. Okay, when you multiply it with the width, then you get the UDL. So that is what is done here. Okay, then self weight And then self weight is taken, self weight of the stringer beam is taken as 10% of the dead load, this one. So it is becoming 1.2. Okay, total UDL you have got 13.4. Then WL square by 8 and WL by 2 formula, you get the bending moment and shear force. Please type Y if you have understood this part till now. Okay, okay, all right, I can proceed. So after this maximum dead load moment, maximum dead load shear force, let us go to the live load. So for stringer beam, the obviously if I let me go to the paint once more. People will move along this direction, isn't it? This is 4.2. So when the vehicle, this tank will move like this. Okay, this one is 3.6. Okay, this tank will move like this. So bending moment will be highest when the tank is at the midpoint. Okay, so this tank, the bending moment, for the highest bending moment, it has to be at the middle. And for highest shear, it has to be at one of the ends. So that is what is shown here. Okay, the first one is for bending moment, this one, and the second one is for shear. Okay, then intensity of load is, you see 350. Why it is 350? Because we are doing it for one track. Okay, we are doing it for one track because at one point of time, both the tracks of the tank will not fall on the stringer beam. Only one track will fall on the stringer beam. Okay, so one track, the total load is 350, and overall load of the IRC class AA track vehicle is 700. So the load by length is the UDL, right? So 97.2 is the UDL. Okay, so if we consider this diagram, okay, the UDL that is falling here is 97.2. Okay, this is nothing but the tank. And for highest shear force, the tank should be here. Okay, so when you calculate the bending moment formula, you consider this diagram. When you calculate the shear force, you consider this diagram. So the live load bending moment, this one, this is what? W into, it's L by 4, so it's L by 2 divided by 2, isn't it? 2.1 is what? 4.2 by 2, isn't it? I mean, if I write it down, 1 second. So if I this is what 3.5 into 2.1 by 350 into 2.1 by 2. That means what? 350 into yeah, I am recording. No need to worry. So 350 into 4.2 by 2 divided by 2, or you can say 350 into 4.1 by 4, which is what? W L by 4, isn't it? So that is the uh, thing that is going on here. Okay. So any doubt? Please, you can mute your mic. If you have any doubt, you can speak up, or else you can mute. This is for the point load. Okay, 350. Then the load is falling at the center. Okay, so generally, if I just try to calculate it, at this point I need, so there is one load of UDL coming here, isn't it? We need the load moment at this section. So this into this plus minus this into this, we get the moment. Okay, the first term in the equation is this one. Okay, and the second term is, first one is this one, and second one is actually this one. Okay, so ultimately we get this equation. Okay, this one. And for live load shear, for live load, maximum live load shear, it will be WB by L. Okay, WB by L. So if I try to write it here, it becomes, for maximum shear, the load is at this point, isn't it? This is total 4.2. Okay, the 350 is coming somewhere here, and this is 1.8. This is 2.4. So if this is B and this is L and this is W, the shear force at this point will be WB by L. So 350 into 2.4 by 4.2. So that is what is going on here. Okay, so moment after this one, we have got the maximum live load moment, live load shear force. Then we have got the dead load moment, dead load shear force. Then I have given an impact of 25%, so I am adding it. Okay, then shear also I am giving an impact of 25%, so this one. Okay, then ultimately moment will be what? Dead load moment plus live load moment. This is the factored moment. So this is, we get shear force also. This one is the factored shear force, and live load plus dead load, factored shear force we are getting. Then now we reach the place of steel design. Okay, now we have reached steel design. Here what we will do is, whenever you design a beam, I hope you have gone thoroughly through the videos. Whenever you are designing a beam, you have to find out the plastic section modulus required. Then you have to consider a beam whose plastic section modulus is higher than the plastic section modulus required. So the formula of plastic section modulus, already if you have seen the videos you will understand. Moment, okay, into resistance factor divided by yield stress, then you will get this one. Okay, then you have to go to the IS code, IS 800, and go to the table at the back side of IS 800 and see which section has a higher plastic section modulus. So here they selected this one, which has a higher section modulus, which is this one. Okay, so first one, required plastic section modulus, then select an I section whose section modulus is, plastic section modulus is higher. Okay, now depth of the web is what? Total depth minus 2 into thickness of flange plus radius of the root. I hope you have gone through the concept of radius of the root in your in the video. Please reply why if you have understood what is the radius of root. Okay, just one. Just two have studied or what? Okay, I will not go further into the radius of root. It is properly given in the video what is radius of root. So depth of web you will get. Then remaining steps are same as what we are similar to what was there in the video. We have to classify. You have to classify the section: plastic, semi-compact, compact, like that. So for that you have to find this, then you have to find this. Okay, then you have to find this one. Okay, then after that you get that the section is compact. Okay, then you have to find this value. D by TW, which is less than 67 epsilon naught. Okay, so this in this formula, this is there in IS 800. So that's why I have told you that you have to bring IS 800 to your examination hall also. Okay, otherwise, sorry, there will be no examination hall. You have to keep it handy. Okay, so you have to know where this clause is. Okay, so for this moment, you will calculate using this formula. Then the moment here it is seen that the moment is higher than the moment applied. This is the moment capacity, okay, which is higher than the applied moment. Okay, so now you have to check for shear. So in moment it is safe. Okay, I would recommend that you please do check these parts. Okay, do check it. Don't just simply try to memorize it. Do check it, okay, and match it with your IS 800 and try to find out the section classification yourself. Then you go for shear. For shear, this is the applied one. Then this is the design capacity of shear. So in this capacity, Fy, you know, this one is resistance factor. Area is what? Area is the depth of web. This H, depth of web. This one, depth of web into thickness of web. It is thickness of web. This one, TW. Okay, so this is done. Then you see that this is more than the applied shear force. You get the capacity. Capacity is more than the applied shear force. And you should also check that it is there in my video also that even 60% of your capacity, this 1.6 of your capacity, should also be greater than the applied shear force. So that should also be there. Otherwise, it is a condition of high shear. Okay. So I don't know why I'm coughing so much. I may have to go to quarantine center. Maybe. Don't know. Then design of cross girder. This is done. This is all about the stringer beam. Okay. So two designs are done. Then cross girder. So which one will be the cross girder? Let me just show you. So if if this is the 7.5, okay, and we are going like this. This is 4.2. These are the stringer beams. So if I look from this side, okay, if I look from this side, then this, whatever you will see, if you, suppose that you are looking from this side, then this you will see, isn't it? The stringer beams will be placed like this. Okay, so this is the cross girder. Okay, so that's why if you see here, the length is 8.7, isn't it? Now we have to give a consideration of impact, which is 10% for all spans for tracked vehicles. Now that will be done later. Now this is the diagram. Okay, so again, now for the UDL due to the deck slab, in the stringer beam, what we did, 6.5 into 1.875. Here it is 6.5 into 4.2, perpendicular direction. Okay, because the cross girder is perpendicular to the stringer beam. Okay, so this value will be taken perpendicular. to 1.875. Okay, so that's why we are taking it as 4.2. Then self weight of cross girder is taken as 0.2 of L plus 1. Okay, so it is 0.2 into 8.7 plus 1, which is 3. Ultimately, the total UDL is this one. Okay, then the dead load. Okay, dead load, we have already got this one 1.2 previously. Okay, 1.2 we have got 10% here. You can say, wait, this one. This is self weight of the stringer. Now this weight of stringer is also falling on the cross girder. So that's why this stringer into the length perpendicular, then you get the total load. Okay, and connections, etc., like bolts and all, 0.36. It is I have to see from where they have taken, but maybe there is a like I have forgotten actually. Maybe there is a clause somewhere. I will look into it and I will tell you. So total load of stringer, just as you just try to know that total load of the stringer on the cross girder is 5.4. Okay, so now ultimately what you have got, the cross girder, the stringer is giving a point load of 5.4 everywhere it is. Okay, stringers, 5 stringers, so 5 point loads. Then this is the UDL. Okay, the UDL is along the whole length. And from this, you have to calculate the maximum dead load moment and dead load shear. So this formula, it's like a strength of materials problem, finding the bending moment, okay, and finding the shear force. So you can do it yourself. Okay, find the moment at the end. Okay, find the moment. Sorry, not at the end, at the midpoint. That will be the maximum dead load moment. It is already shown. The calculation is already shown here. But still, you do it once. Okay, do it once. Then for live load, see this. When you are looking at this cross girder, okay, this is the cross girder, and this is the tank. Okay, you visualize it like the tank is. You are in front of the tank. Okay, you are in front of the tank, and uh, these are the two tracks of the tank. Okay, and the tank is moving towards you. Okay, and this 2.05 is the center to center distance between the two tracks of the tank. Why we are placing it at the middle of the cross girder? Because then only the moment will be higher. And for shear force on the cross girder, the tank should be at the sides. Why we are keeping a gap of this much? Because if you see the diagram of IRC class AA, there is a spacing that you need to give. Okay, from the edge to the outer track. Okay, to the outer track. So that spacing is this one. So that's why you cannot go beyond this. Okay, so this is the farthest you can place. Okay, So since you cannot go beyond this, you have to find out the shear force here. Okay, and then if you see this diagram, it is a strength of materials problem. Find out the moment, and this is also a strength of material problem. Find out the shear force. Then impact of 10%. So we have multiplied, we have increased it by 10%. Moment and shear. Okay. So now dead load moment plus live load moment into 1.5 factored moment. Dead load shear force plus live load shear force into 1.5 factored shear force. Okay. So this is the calculation of the loads for the you can say the cross girder. Okay, now actually I have a meeting at 6:30, so I'll do one thing. We will complete it tomorrow, and then we will go to rocker. Okay, so by 21, hopefully we will try to complete this problem and the rocker problem. Okay, so uh, will it be fine? Let us try to catch up till 23rd. Let us see how much we can finish. Okay, then let us meet at around in like 3-4 p.m. I will let you know the time. Okay, so thank you.
Thank you, sir.
Okay, thank you.